Okay, hello everybody who might be watching this. This is going to be a live stream where the first half an hour between now, which is 7:30, and 8 o'clock, we're going to be looking at GCSE and a last bit of stuff for paper 2, which is tomorrow for GCSE. Then 8 o'clock, I'm going to move on to some stuff for A-level physics. Hello to everybody. It's great to see lots of familiar people in the chat. Tamadola, Hyperslane, Anissa, Cameron. Hello everybody. I must say at the moment it is a horrible evening outside. It is dark, it's windy, it's raining, which is perfect because that means you're not missing out. By not being out with your friends in the sunshine, you know that basically tonight is your last chance to do some revision. Now, I must say, for anybody watching this live or anybody who's, maybe looking at this on kind of catch up, I've put a link at the top of the chat to one of my videos I made last year. And this is some other kind of content I did a couple of years ago where I basically go through all of the paper 2 content, in this case for AQA, in under an hour. So if there's anything you need to do last minute, I can definitely teach you a few things, get you some extra marks potentially, or maybe just make you feel more secure in the knowledge that you currently have. So the first bit of the live stream, we're going to go through one of my papers. This is one of my practice papers that you can buy at my shop, which is physicsonline.shop. I've got 6 extra practice papers for paper 2. We're just going to quickly go through a couple of questions about waves, and then I thought I'd do some multiple choice questions on Phys Quiz, just to kind of cover lots of different topics. I will be keeping an eye on the chat. Timodola says, can we do some magnetism? Yeah, I think electromagnetism is definitely one of the more tricky topics, so we'll be doing some of that. But hello to OK, Evil, James, Roko, Dylan, Muffy, 008. Hello everybody, hope all of you are doing okay. So let's just start with this kind of bit of revision. So this question is about seismic waves, and these are waves underground created when you have earthquakes or lots of Taylor Swift fans in Edinburgh. The first question though is just about what some of these terms mean. So what do we mean by a longitudinal wave? So a longitudinal wave is oscillations of the particles which are parallel to the direction of energy transfer. Often when we do this, we often maybe think about a sound wave, and we can maybe draw the particles kind of sort of spaced apart and then closer together. And what we have are regions of rarefaction and regions of compression. And basically the particles are going to oscillate side to side in the same direction as, well, perpendicular in the same direction as the energy transfer. Okay, so it might be a sound wave, or it might be a wave in a slinky, where we get something like this. And again, we've got basically the bits of the slinky just move back and forwards, but again, the energy or the wave direction is like that. Okay, vibration is absolutely fine. Okay, so if you were to put down the word vibration, that's also completely fine. GCSE, vibration oscillation, even at A-level, it doesn't really matter. Is this my final live stream, Maximilian? Yeah, this is going to be my final one. I think this is my 35th evening live stream. I've done this exam season over the last couple of months, and I did like 3 super long, like 3 or 4 hour ones over the half term. So I think this is like live stream 37 or 38. In a way, I'm quite looking forward to not doing this in the evening, although it's obviously great to chat to all of you lot. And also, make sure tomorrow you bring your protractor. Don't forget you might have to measure an angle. Okay, but it's been great to do these live streams, and hopefully some people have bought some things and they've seen my website, and hopefully this just shows you, especially if you're GCSE people watching at the moment, although I've been doing lots of GCSE stuff, I have stuff for A-level physics. So basically I can help you a lot as you go into year 12 and into year 13. Oh, it's really nice with Badger saying that you're going to miss them. Yeah, people, Maximilian, going to miss me. Well, you can still catch up with me in many of my other videos on YouTube. So yeah, don't worry, I will still be there. What do we mean by a seismic wave? Basically, a seismic wave is just a wave produced in an earthquake. So maybe when you've got plates which are kind of moving side by side or over one another, stuff you might have learnt about a bit more in maybe chemistry or geography. Basically, that sends a shock wave that goes through the Earth. Now, there are 2 different types. We have P waves and we have S waves, the primary and secondary. So when a P wave has passed through a particular rock underground, the rock is completely unchanged. So this question, although it's about a seismic wave and that's the context, is really saying, what does this tell us about waves? Basically, waves transfer energy without transferring matter. So even though the particles in the rock might kind of vibrate back and forth, it's not like the rock is moving from one place to another. And it's the same with a sound wave. The air particles just oscillate back and forwards, but that pressure wave is passed along with these vibrations. Chicken Kiev, love that name. Thank you so much. Yeah. Yeah, Rapid YT. You won't miss me. In actual fact, if anybody out there is doing A-level next year, which is great, basically you can still have me here for the whole summer holidays. This is my daily workout book for A-level physics. Buy it now. You can find it on Amazon. It will arrive after your GCSE exams are finished in a couple of days' time. And then I have questions that begin on the 1st of July. You do these questions on the 1st of July, it takes you 5 minutes, do it before breakfast, and then you do those questions on the 2nd, and those on the 3rd, and those on the 4th, and those on the 5th. And just do 5 minutes of questions every day over the summer, and I will hopefully help you prepare for A-level. Right, we then have a diagram showing, looks like a pair of eyes actually, doesn't it, but with some kind of eyelashes. This shows the path taken by P waves and S waves created near the Earth's surface. This diagram took me ages to draw. But basically what we have is P waves. They basically will kind of radiate out from wherever the earthquake is, and they'll pass around this part. Any waves which get here kind of go through this region and then come down here. So basically there's a region where waves are either meeting above it or below it, but what we have here is a shadow zone where no waves are detected on the other side. Now S waves are similar, as in they're going to be created in this, but in an earthquake you have both longitudinal and transverse waves. Now these waves here, you can see, they can't actually go through this section here. They can't go through the liquid core, and that means we have a much bigger shadow zone. So these S waves can only be detected nearer to the earthquake, and they don't travel through the centre of the Earth. So S waves cannot travel through a liquid because they are transverse. Okay, at the point where S waves meet the outer liquid core, the S waves are being absorbed. So they're not being transmitted, they're not being reflected or refracted, instead they're being absorbed. Okay, so I'm just trying to read the question. So Evil, are electromagnetic waves transverse? Yes, electromagnetic waves, you've basically got oscillating magnetic and electric fields which oscillate at 90 degrees to the direction that the wave is travelling in. IDK, I don't know what that means, that name. Okay, you've got a request. I think you should try have a go at the A-level exams in the near future, maybe a little test you can do to see how students handle. So yeah, I know that, I've forgotten his name, Bison Maths. I know he's done A-level maths. I think that'd be really good because it'd be so interesting, yeah, so maybe I should do that. Right. Okay, figure 8 shows the shadow zone where S waves are not detected. Describe how the size of the outer liquid core of the Earth affects the size of the shadow zone. Well, basically, if you had, imagine a bigger liquid core, then that would mean that less of the waves can get through because more waves would be absorbed by this, and that means the shadow zone potentially would get even bigger. So this means that we can actually detect the waves from an earthquake, and we can sort of map backwards because we know where we detect them and where we can't. This gives us an indication of how big that liquid kind of core is of the Earth, because we can't obviously drill down and see it, so we have to work out a way to actually see inside the Earth. So the larger the liquid part of the core, the larger the shadow zone. So that's how the size of the outer liquid core affects the size of the shadow zone. So you have a smaller core, we'd let more waves through to the other side, we'd have a smaller shadow zone. And basically this is the way that scientists and geologists and other people who like rocks can actually look at what's inside the Earth. Okay, figure 9 shows an S wave passing through a section of rock. Again, we saw an S wave is a transverse wave in that last part of the question. The section of the rock on the right is undisturbed as the wave has not reached it yet. So basically, here's a wave moving. So if we think about it, the wave is kind of like this. And at this point, it hasn't actually reached this part here. Label one wavelength on the figure. So the wavelength is just going to be the distance from a peak to a peak or a trough to a trough, or any point like that. So basically, all I've done here is I've labelled the distance. Peak to peak, I think, makes sense. And I've labelled that with lambda, the symbol for that. Okay. Oh yeah, by the way, everybody, if you haven't already done so, make sure that you do like the live stream. I think that's good. YouTube like people to like things. And if you are liking it, that's brilliant. It's amazing actually to see some of my recent videos. They're like 100% likes. So it's like, you know, 200 or 300 people have watched the video. No, a few thousand have watched it. Maybe 10% might like the video. And all of them have liked it. There's been no dislikes, which is incredible. Okay, we've now got a question where we've been given the speed of the wave. We've been given the frequency. Calculate the wavelength. So for this, I just looked at the data sheet. We know that V equals F lambda. Thank you for all the likes, everybody in the chat. That's awesome. We know the wave speed is frequency times wavelength. We've rearranged this to say the wavelength is the speed over the frequency. Now, the speed of waves is quite high in solid materials because the particles are really close together, so they can pass the vibrations on really quickly. Whereas in the gas, the particles are further apart, so the speed maybe of a sound wave is slower in air than it is in a solid. So they travel really fast in a solid. We divide that by the frequency and get a value of 900 meters. So the wavelength in this case is 900 meters. Okay, that was the end of the question. So what I thought I'd do now is, in order to go through as much physics as possible, if you want to look at the rest of these questions, I've got questions. Again, I'm very happy with this picture that I drew of a copper pipe and a coupling. There's questions about moments that come up in this paper. There's a question about a Leslie cube. There's also questions about the way that different coloured surfaces affect the absorption and the emission of stuff. We've got a question about magnetic fields. If you want to buy this, then you can download it in my shop tonight. Okay, so these are the papers. If you want to have some last minute testing, you can just basically buy these. Even if you just look through my work solutions, when you buy it, you get the paper, you get the mark scheme, and you get a set of work solutions. So one of those might be useful. Okay, right, before we go into A-level, which is 8 o'clock, so let's have a look at some multiple choice questions. Now, this is not like endorsed by the person who did this, although I think he's a great teacher and he's done a great app. This app is called Fizz Quiz. Okay, you can buy it tonight. I'm going to put to the side, because somebody in the chat is going to ask, what's it called? It's called Fizz Quiz. Okay, and basically there's loads and loads of questions. So if you want to play along at home, we're going to look at some questions. Now, I think generally, the thing that people struggle a lot with is electromagnetism. So we're going to have a look at some of these questions. Again, if you want to at home, please put, if there's 3 questions, maybe put just A, B or C, so like the top downwards. Ritrack saying that you now have to go, now you have a physics exam. Good luck. Hope that all goes well. Charlie saying conflicted between physics or computer science for A-level, and you enjoy both. Depends what you want to do, but I'd say that a lot of people who do physics end up becoming computer scientists. A lot of computer science you could probably teach yourself if you're motivated. It's a good question to have, though. Okay, do you need to describe a split ring commutator? Is a split metal ring and contains conductor brushes in GCSE? Yes, so a split ring is used in a DC supply, so it might be a DC motor or a dynamo, which is a DC generator. And yeah, you need to kind of have a picture of what it's like. Okay, so a magnetic field has a direction. Is it true? Is it false? So is it A, B or C? What do you reckon? What do you reckon, A, B or C? James says C. So do magnetic fields have a direction? They do. Magnetic fields have a direction, and the direction is from north to south. So here the answer is C. Cool. A material which becomes a magnet when placed in a magnetic field is called is it a permanent magnet, a solenoid, an electromagnet, or an induced magnet? So what do you call a material that only becomes magnetic when it's in a magnetic field? Say, for example, you had a block of iron or a block of steel. You put that in a magnetic field. That's what we then call D, which is an induced magnet. Okay, next question. The Earth has its own magnetic field. Well, that's true. All of you know that. The next question says, the red tip of the plotting compasses is north. Which side of the bar magnet is north? So, if the red part here is north, that's going to point to the south end. And that means I say the green side is going to be the north side of that magnet. Okay, when removed from a magnetic field, an induced magnet, right, when removed from a magnetic field, an induced magnet, so maybe a piece of steel, what happens? Does it gradually lose its magnetism? Does it lose all its magnetism, stays magnetized? I reckon it loses all its magnetism. Excellent stuff. So the answer for that was B. Magnetic material is one which is attracted to magnets, becomes an induced magnet when placed in a magnetic field. Okay, so a magnetic... Okay, so that's a difficult question, isn't it? So what do you reckon we say? Is attracted to magnets and becomes an induced magnet when placed in a magnetic field. Okay, what's going on here? People are saying error, try again. Right, the magnetic field of a bar magnet is strongest at its poles. That's true. And you should have an idea about what the field line looks like. And obviously we can model that using things like iron filings. A magnetic compass has a small suspended magnet in it which aligns itself to the Earth's magnetic field. So all of you out there who might have done things like 10 tours recently, or you've been doing D of E and things like that, you have this magnet, and the reason it points north is because it does align with the Earth's magnetic field. The further you move away from a bar magnet, the magnetic field, does it reverse direction, become weaker, become stronger, or remain steady? Well, basically, the field lines get further apart as you come away from this magnet, especially a permanent magnet, and that means it becomes weaker. Okay, right, so I think a lot of people are getting the right answers in the thing there, but those questions were fairly straightforward. Let's have a look instead at the motor effect. This is using Fleming's left-hand rule, so make sure you do use your left hand. Okay, which rule can be used to determine the force direction on a current carrying wire in a magnetic field? So this is using Fleming's left-hand rule. Are people getting errors at the moment for some reason in the chat? So Fleming's left-hand rule is the correct answer. So the answer is D. Well done, James, and other people. Right, I think there might be, for some people, there's errors in the chat on YouTube. I think it's just a YouTube thing, but some people are, some people aren't. Error, try again. I'm not quite sure why that is. Yeah. Okay. If you are there though, I know that if you keep trying, obviously some people's messages are getting through. It won't let you send answers, but yet I don't know, why is that? Why would it be doing that? Okay. The magnetic field around a solenoid. So a solenoid is just a coil of wire that can carry a current. Right. Are people saying that it won't let you comment, but yet I can read your comments? I can basically see what people are saying. YouTube seems to be broken. Maybe just there's so many people revising last minute on YouTube that YouTube's just become overburdened by people doing last minute stuff. Maybe it's a storm. Yeah, maybe it's just like the weather just saying like, look, stay inside, get on with your physics. So the magnetic field, yeah, this is weird, like only about 1/10 of the comments are coming through. Okay, well, let's try it. Let's sort of everybody who's watching this at the moment, I don't know how many people are actually here. 62 people, so there should be 62 people who can comment. So the magnetic field around a solenoid, is it similar to a bar magnet? Oh, it is. I've already clicked that. Right. The magnetic field inside a solenoid, is it weaker than outside, stronger than outside? Is it weak, or is it zero or non-existent? So basically a solenoid is this coil of wire. When you pass a current through it, when you have these moving electrons, there's this associated magnetic field. And inside the solenoid, what we find is that there's a kind of concentration of field lines. So that means it's going to be stronger than outside. And that's why we use solenoids with things like Helmholtz coils to generate really strong magnetic fields. Okay, electric motors often have curved pole pieces so that the magnetic field is... okay, this is difficult. Okay, so electric motors often have, rather than having like flat magnets on them, they often have like a curved magnet that goes around the coil inside. Is this, so they are, the magnetic field is radial or the magnetic field is uniform? Okay, that's difficult. I'm going to say, oh, there we go. Radial, so the force is always perpendicular to the coil. Yeah, okay. In which direction is the force on the wire? So what we have here is a current. We've got a wire held in a field. So we're going to use Fleming's left-hand rule. I'm just going to zoom out slightly. We're going to line up my first finger with a magnetic field, which goes north to south. So it's like here. And then my second finger is pointing in this direction. So I reckon, looking at first finger field, second finger current, my thumb is pointing down, and I would say that that is downwards. So hopefully that's all good. For a current carrying wire to experience the largest force, the wire must cut across the magnetic field lines perpendicularly. That is true. So when you think about Fleming's left-hand rule, there's a 90-degree angle between your thumb, showing the direction of the force, and your first finger, and then another 90 degrees over here, and then another 90 degrees there. So when things are perpendicular, that's when we get the biggest force, and so that one is true. Well done, James. I think James is okay. Yeah, for some reason, some people's chats just aren't coming through at the moment. Which of these will increase the strength of a motor? Select one or more. So if you want to have a stronger motor, then you can increase the number of coil turns. So there's more turns on that coil. We can increase the magnetic field strength, and we can increase the current. So by increasing B, the magnetic field, increasing I, and increasing the number of turns, which is going to affect the length effectively of wire in that field, those things will make the force bigger. So F equals BIL. How do you describe how to use the left-hand rule in a 6 marker? Great question. I would say that if you're going to describe it, you need to say what each finger represents. You need to say you hold the fingers on your left hand at 90 degrees, and then you say how you'd line up the first finger pointing from the north to the south pole, the second finger in the direction of conventional current, and then that lets your finger point in the direction that the force would be applied to that wire. Okay, brushes are... Okay, that's a really nice question, actually. So basically, what you sometimes have is you've got two surfaces which are moving, but you want to have an electrical contact between them. So basically, imagine this is like a piece of wire. Okay, so you've got like the outer kind of bit of rubber or plastic around the wire. Here you've got the wire, and basically that wire is made out of metal. So maybe this is kind of copper or something. And you want to maybe connect this to something which is spinning. So something that might be spinning might be part of a... So this one here is supposed to be my split ring commutator. Okay, so this thing here has 2 bits of metal, which are maybe made out of copper. Okay, and that's going to be rotating, and obviously this is going to be connected to the coil in that circuit. And what you need to do is have some kind of connection here, which is going to have 0 friction. And that's where you basically have what's called a brush. Sometimes it's called a brush, sometimes it's called a bush, but basically this thing over here is often made out of something like graphite, because graphite is a conductor, and it's made out of many layers, so it's quite slippy. So basically what this can do is this thing here is basically a brush. And it basically allows this metal, which is going to be spinning around, to move next to this without just having metal on metal, which would just wear away. And then once it wears away, there'd be a gap here, and then electricity wouldn't flow. So what you have is a brush, which is basically, it allows the electricity to be conducted from here to here. Okay, they might be spring-loaded, yeah, because that means that there's always going to be a connection between these two sliding surfaces. Okay, in Fleming's left-hand rule, the first finger indicates direction of the magnetic field. Let's see if it just lets me do this. Magnetic field. I probably should have written it out fully, shouldn't I? Okay, what is the symbol for magnetic flux density? So is it F, B, T, or M? So anybody in the chat, do let me know if the chat is working, which answer you think it is. Is it A, B, C, or D? So what is the symbol for magnetic flux density? So James says Tesla, but Tesla is the unit for magnetic flux density. Anissa, great stuff, saying B. So in the equation F equals BIL, B is the magnetic flux density, and we measure that in Tesla. Okay, so the symbol for magnetic flux density is a B, but the unit that we measure it in is T. Okay, so that's the symbol to represent it. That's the unit. Okay, B. An equation relating force, magnetic flux density, current and length of a wire is, well, we know it's F equals BIL, so we could also rearrange that to say B is equal to F divided by IL. And looking here, we've got F over IL, so that must be the correct answer. In a loudspeaker, the coil, actually that doesn't quite work. Okay. So the strength of a magnetic field around a current carrying wire can be increased if the current is increased, the resistance is lower, the voltage is increased. So surely if you had, yeah, I think if you increase the potential difference or you reduce the resistance, that would also mean that the current increases. Okay, Fleming's left-hand rule can be used to determine the magnetic field, current or force direction if the other two are known. Yeah, so if you know two of the three things, you can line up your fingers, and that means that allows you to find out other things. And an electromagnet is a solenoid with an iron core. So if you put an iron core into that solenoid, it then behaves like an electromagnet. We'll do one more question. The part of the electric motor shown by the arrow is called. So this one over here is something that I think it's really hard or really important to remember. So what we have here is something which is split, and what we have is a split ring commutator. Adriel, James, my hair, lots of people there saying it's a split ring, because it's basically a ring of metal that's been split that way, and it's a split ring commutator. Okay, I reckon we'll end it there. So basically, if you're watching this now, you are in a great position. You don't have long left. In less than 24 hours for a lot of you, that will be the end of your GCSEs. And that means any exams that you ever take for the rest of your life are going to be completely optional, because you'll be the one who's decided to do those exams. You know, GCSE are very much the last things you have to do in your life. So yeah, for a lot of people, unless you're doing food tech on Wednesday, or you maybe have statistics on Monday, this could well be your last GCSE exam. Again, you know what you're doing. All of you have done multiple exams this year. You know where you're going. You know the equipment you need. Make sure you have your calculator. Make sure that you have your protractor for physics in case you need to measure an angle, or maybe do a scale diagram when you're looking at forces. But basically, all of you by this point are in a great position. And if you do want to be doing A-level physics next year, then I think it's well worth doing. It's a lot more interesting than GCSE. And of course, if you want to spend another kind of 5 or 10 minutes listening into the stream to kind of see some of the more interesting questions and the chat from the A-level physics people, yeah, don't be put off by the A-level people saying it's hard. They're just stressing because they're year 13 and they've got their big exams. So Swizzy says, don't do A-level physics. I guess you have your exam in a couple of days. Honestly, it's not that bad. My last thing is go and buy my book. It is A-level physics, the daily workout, book 1. This is your perfect bit of transition work to do before you start A-level physics. And of course, I have videos that support everything in A-level physics. And I've got a lot more coming in the future. Okay, so let's start with some questions, A-level people. Let me know if you're A-level in the chat. I think the chat wasn't working before for some reason. I'm not quite sure why that might be. So these questions here come from one of my practice papers, which you can buy. Again, I've said this a few times, you can buy this in my shop, which you should all do, because it's only less than a tenner. You can get all the papers, and that could really help you as you're working through stuff over the weekend. Now, this question here is something that you won't have necessarily done in school, but basically we've got a steel bar, a square cross-section, so it looks like this at the end. Okay, and basically it's got a width of 3 millimeters, so that's how wide it is, and because it's a square, then it must have a thickness or a depth of 3 millimeters as well. We've got a length sticking out from the cantilever. We put some masses on the end, it bends down a bit, obviously. Now, a student, that's you, has been provided with an equation which relates to quantities involved in the deflection of the steel bar. So it basically says y is equal to FL to the n over 3EI. Now, nobody doing GCSE or A-level will have seen that equation before, but the whole point is that it's an unfamiliar equation, so everybody is basically, everybody's seeing an equation for the first time. And I reckon that, yes, this is for all exam boards. Although I've called this paper 3A for AQA, you can buy the same pack of questions for OCR and EdXL on my website. And basically, this is just a question where it's saying, here's some new information using standard lab equipment that you will have used beforehand. Here's some new information, again, that kind of maybe links back to other stuff. So we've got the Young modulus. There's an unknown power, n, and I is a constant called the second moment of area. It might be, if you are doing the AQA engineering option, I might be familiar for when we're looking at things which are kind of like rotating and angular, things like that. But for the rest of you, it doesn't matter that you haven't seen this before. The first question, though, is just like a standard paper 3 question. Outline a method for measuring the vertical deflection of the beam using a meter ruler and any other equipment. So basically, what would you do to actually measure this distance here? Well, I would basically get a meter ruler. I'd make sure that it is vertical using a set square, and then I'd clamp this in place with some kind of retort stand, and that means it's not going to move. Okay, so basically, this is just simple stuff. So you've got to think about clamp a ruler, and you ensure that it's vertical with a set square, and that means you know it's perpendicular to the ground. Okay. Masharaf says he saw a video of me eating baked beans for a GCSE practical and radiation. Yeah, like cold beans, don't like them hot. But yeah, I did eat the whole can of beans. Yeah. Right. The next thing is you need to measure the level when there's no load. And of course, you need to make sure you keep your eye in line with the thing you're measuring. You need to make sure that this is really close to that, so there's going to be less chance of parallax error. And basically, you basically need to measure unloaded, then keep eye close to reduce parallax. So again, all standard stuff. So this first question is basically 2 easy marks. It's just about how you would make your measurements better. Am I going to be doing relativity, Michael? Not tonight, but if you do want questions about relativity, I do have them. Or if you want to kind of see like some work solutions to that, or if you want me to explain relativity again, I do have videos over at alevelphysicsonline.com where you can find stuff for the optional topic. But I'm afraid I can't do everything tonight. Okay. We then have the student changes the length of the bar going past the edge of the bench. And basically, if you make it go further out, it's going to bend more at the end. It's kind of like almost like obvious stuff. They record values of the vertical deflection y. They keep the size of the force F due to the load constant. So basically, they get this bar and they just push it further and further over. The first thing, again, is an easy set of 2 marks. So all you need to do is take the log to the base 10 value of these. So we've got basically the log of 0.8, which is minus 0.097. And then we've got the log of 1, which is just 0.000. I mean, it is 0, but I'm just going to keep the same number of decimal places as we have up here. So they're all to 3 decimal places, we can see that. And then, of course, you do the same over here. So you've got the log of 0.063, which is minus 1.20, and the log of 0.123, which is minus 0.91. So again, keeping those, I generally reckon for this, maybe keeping to the same number of decimal places, but of course, you could also give it as 0.910 to 3 significant figures like that. Either of those is acceptable. Okay, so you could have another 0 in the end. But basically, that's easy marks. And then there's going to be even more easy marks, which is basically using the data up here. We just need to plot it using the axes provided. So for that, we just start over here. So we've got log L on the x-axis, and then we've got log y on the y-axis. We can see also that here's 0 and it goes down to minus 8, and it's minus 1 down to minus 3. So 0.69 is going to be about here, minus 3, so we've got a point here, and then we've got point about here, minus 2.222, so that's 3, 5, so it's going to be around here. This is probably a boring thing is watching somebody plot a graph, but I guess lots of people, whereas it's going to be around here somewhere, and 1.2, about there, and then 0 and minus 0.91. So it's going to be like that. Is that right? What's happened with the chat? The chat isn't working. I don't know what's happening. I think YouTube have messed up. I know that there's lots and lots of people on the chat at the moment, and I know the chat, for whatever reason, just isn't working. So I'm not quite sure why that is. However, if all of you could like the video now, if everybody could like it manically, I think there's a heart button. If you click on that, or hundreds, there's like faces and things. If everybody could start clicking that for the next couple of minutes, that would be amazing, just to see if anybody's actually there. So, okay, people are liking the video. I know you're out there, people, but I know it's difficult to ask questions. So again, even though you might be doing paper 3, a lot of the skills are going to be fairly straightforward. You can obviously then use your pencil in the exam and your ruler to draw a line. There will be a question, I'm sure, where you need to fit something to y equals mx plus c. So I don't know what's happening with the chat, but people can say in the chat that the chat's not working. So I don't know exactly what's going on. Okay, so I'm just going to draw in a line of best fit here, something a bit like that. And often if we're drawing in a line of best fit, then we're going to have to work out the gradient for something. So some easy marks there. Use the graph to calculate the value of the unknown power n in the equation. Okay, this is where the physics comes in. So basically, yeah, Chicken Kiev, you're sending basically 10 messages, and the first one, only one of them gets through. Right, so on the first part of this, it did say that y is equal to, where is it? I've lost my bit of paper. Y is equal to FLN over 3EI. So I'm going to say that y is equal to L to the n times F over 3EI. Okay, so that's the equation that we're starting with. How can we find out the value of n? Well, what we need to do is maybe take the log to the base 10 of both sides. So we can say that log y is equal to n log L plus log of f over 3ei. Okay, so all I've done is I've taken this, I've taken the log to the base 10 of both sides, and we know that we should be doing that because we've plotted log y against log L on the graph over here. Now on the graph, on the x-axis, we have log L. So this is on our x-axis. On our y-axis, we've been plotting log y, so that's on the y-axis. So we've got that on our y-axis, and that means this is equal to mx plus c. Okay, so what does that mean? Well, basically, if we work out the gradient of that line, that's going to be equal to n, the thing that L is raised to the power of. Okay, right, Scarface, it just doesn't let people send stuff through. Chat just mad, airing everyone. So I would say, I am reading your chats. I don't know what's going on tonight. I just think that I've done so many live streams, it's said, you know what, yeah, no idea what's going on. So yeah, basically, if you do send me a message, and I will try and read them out. I am reading them as I'm doing this, but hopefully this is kind of making sense. And again, if you like what I'm doing, just keep liking the video. It's always nice to see the hearts kind of sort of floating up at the side. So we need to work out the gradient, which is going to give us the value of n. So we can do that by looking again at drawing a triangle onto our graph, which is what you do every time, I'm sure. And then, of course, to work out the gradient is like basically GCSE maths or GCSE physics. It's not difficult at all. Thank you for the hearts, everybody. Appreciate that. So the gradient n is going to be equal to the change in y over the change in x, which is equal to this value over here, which is minus 1.1 minus 3.0 divided by 0 minus 0.7. So basically that's minus 1.1 plus 3 divided by 0.7, which is equal to about 2.7. Now it says, I think on the first part of the question, that I keep throwing away somewhere, that n is an unknown power. So we've basically got a value for n of about 2.7. So I would say that you could either give a power of 2.7, or it could just be equal to like about 3. So 2.7 is fine. Often when we raise something to the power, it's either to a half, a third, a 2, or a 3, or maybe a 4. But yeah, basically all we're trying to do, I sort of did it longhand, is you'll be given an unknown equation. I guarantee it. You will then somehow have to fit that into the form y equals mx plus c, where the gradient of the graph is equal to some constant in that equation, and maybe potentially the other value, like the y-intercept, will allow you to find another thing. So it said the load using the experiment was such that the force was 5 newtons. Calculate a value for the second moment of area, I, of the steel bar from the data provided. Include a unit with your numerical answer. So we know that the y-intercept c is going to be equal to log of f over 3ei. Okay, now in the question, we know that the value of force is 5 newtons, so we've got the value of F. We know C, because we can work it out from the data, because we can obviously work out the value of C on this graph over here. And C, the y-intercept, is when the value of y, or basically when on the x-axis, x is equal to 0. So actually this value here, up here, is going to be the y-intercept. So that's the value on the y-axis when x is equal to 0. Does that make sense? So we know that the value of c is equal to minus 0.9. Oh, have I made a mistake? Yeah, that value up here, it's not minus 1.1, it's minus 0.9. So let me just work that out again. So minus 0.9 plus 3 divided by 0.7 is actually equal to 3. Excuse me for messing up that. Honestly, the gradient should be the easiest thing, and I messed it up. Okay, right. So yeah, Octazuka, minus 0.9, Anch. Yeah, all of you, I'm sure, are saying this in the chat, but obviously I haven't been able to see the chat, so apologies about that. Okay, so we know the y-intercept is minus 0.9, and that's equal to log of the force, which is 5.0, divided by 3 times E. Now, E was given to us, I believe, at the start. Again, I should stop throwing this paper away. It says that E, the Young modulus of steel, is 200 gigapascals. Of course you knew that. Any mechanical engineering students, the number 210 GPA should be familiar to you. So the Young modulus for that is 200 times 10 to the 9. And then we're going to multiply that by I, our unknown quantity. So then we just have a simple case of plugging some numbers in. The thing I'd do, first of all, though, is I would raise both sides to the power of 10. So basically, we can say that 10 to the minus 0.9 is equal to 5.0 divided by 3 times 200 times 10 to the 9 times I. Okay, so we can just bring I up here and bring that over there to say that I is equal to 5.0 divided by 10 to the minus 0.9 by 3 times 200 times 10 to the 9. Okay, hopefully that's all making sense. So let's do that. So we've got 10 to the minus 0.9 So this is giving me an answer equal to 6.6 times 10 to the minus 11. Okay, so maybe this is probably worth more than 2 marks. Okay, so basically what we're doing here is we're saying that our y-intercept is equal to log f over 3 EI, which is what we worked out when we kind of rearranged the equation that we were given earlier on. I've kind of done a bit of a long-winded way of doing that, but we've got a value for I. Now, in terms of the units, we know that we had this equation at the start that says y is equal to L to the n f over 3 EI. Now, if we rearrange that, we can say that I is equal to L to the n times f over 3 EY. What we can then do is think about what units everything might be. So, L is going to be our length in meters, but we know that n is equal to 3, so that's going to be L cubed. So the units for L cubed are going to be meters cubed. The unit for force is a Newton. We're going to divide that by 3, which is unitless. The Young modulus is going to be stress over strain, and stress is basically newtons per square metre, and then y is a distance measured in meters. Okay, so we've basically got newtons divided by newtons. We've then got meters cubed divided by meters to the minus 2, which is meters to the 5, divided by meters, so that's equal to meters to the 4. So the unit for I is going to be equal to meter to the 4. As Badja Alamin says, perfect, great stuff. Okay, does that help anybody, or have I just muddled things? If you find that there's anything there that I haven't really maybe explained that clearly, I do apologise. If you want to, though, you can buy a set of these in my shop, physicsonline.shop, and in the paper it does come with work solutions like this. So this is basically a neater set of my solutions I've kind of rambled on about tonight, and basically by looking at this, that can help you answer similar style questions that potentially could come up for paper 3. Scarface, yeah, that was a lot for 2 marks. I suspect in the exam that you're doing on Monday, there'll be a lot more generous with the number of marks available. I just wanted to fit it in with the kind of sort of the mark scheme thing. So yeah, But then on the other hand, sometimes you do get real exam questions where you do a lot of work for 2 marks. Okay, do I think AQA paper 2 was the hardest new spec paper? Yeah, I think for a lot of people, and I've seen a lot of the questions, I think it wasn't so much the difficulty of the questions, it was the fact that each question took so long that most people ran out of time. But the thing that you have to remember is as you go into your exam coming up on Monday, if it's a long question, skip it, move on, do the easier questions which might well be later in the paper. Yeah, don't worry about clearing at the moment. Just remember you've got to get through Monday. Once you've got through your exam on Monday and you've finished your A-level physics exams, then you can even, see how it goes Monday before you start panicking about clearing too much. Okay, I reckon paper 3A is going to be fine, and I reckon the optional modules are going to be fine as well. I reckon they've had probably the same team doing the optional modules for years and years, so they're fairly consistent. Yeah, but apart from that, okay, Alison jumps revamp. Is that like mountain bike jumps that you're digging or something, is it? This man and Zed Physics have absolutely saved my physics grade. Thank you. I hope something that we've done has been useful. There's some stuff we might do together next year, which could be cool. So if you want to stay informed, then make sure you do subscribe to me on YouTube and obviously subscribe to Zed Physics, and we'll let you know what we're doing. Okay, apart from that though, Octazuka, bless me and Zed Physics, thank you so much. If there's anything else you're not quite sure about, don't forget you can head over to A-Level Physics Online, or you can just search on YouTube and find another video where I do explain most things. And apart from that, all I can say is good luck. It's been a pleasure teaching lots of you or helping you out. I mean, your teachers have done all the work. Maybe they've written all the reports and marked your tests, but hopefully some of the resources I've got have been useful, if that's books, past papers, the videos. But yeah, apart from that though, all of you, good night, and it's been great to chat to so many people over the last couple of months, and I really, really hope that paper 3A goes well when you do it on Monday. So yeah, thank you very much, and this is the last live stream before your A-level exam, just because I'm away this weekend, so I can't do a video on Sunday. So yeah, slow-mo, what is up thrust? There's a video at A-Level Physics Online where I think I talk about what it is. Thank you everybody.